Welcome, everyone. For today's prep, we're going to see how to calculate definite integrals using the fundamental theorem of calculus. And, well, let's start with this fundamental theorem. Now, before we read through it, this gadget right here, we call this the definite integral. So we actually haven't looked at the technical definition of this. So we're going to first see how to calculate this thing. We'll look at some interpretations, some applications of what this gadget actually calculates for us. And then we're going to be looking later on at the precise definition of what this definite integral actually is. So first, we're just going to get some practice how to calculate this gadget that we call the definite integral. All right, so that's what this is. This is our definite integral right here. And it uses a lot of the similar notation that we've seen for antiderivatives and indefinite integrals. So let's kind of go through just some of the terminology here that we're seeing. So we're going to be integrating a function, f of x. So we call that the integrand. And for our purposes, this function that we're integrating, we're going to assume that it's a continuous function. And we're looking at this closed interval from a to b. So we have these limits of integration. So we call a here the lower limit of integration, and we call b here the upper limit. And together, they're the limits of integration. And we see we have our integral sign that we're kind of borrowing from our indefinite integral. So we have our integral sign here. And then we have our differential dx at the end, telling us that our variable here is x. All right, so this gadget here is our definite integral. And how do we calculate this? Well, the way we calculate it is we need to know an antiderivative for our function. So we need to know an antiderivative for this function. And then once we have that antiderivative, we take our upper limit, we plug it in. We take our lower limit, plug that in, and then we subtract. And like I said, we're just going to get a little practice calculating these gadgets that we call definite integrals. And then we'll look at some applications, how they're used, and then we'll look at the precise definition. The precise definition's, a little more complicated. It involves limits and sums, and it's got a whole bunch of stuff going on. So first, I want to get a little practice calculating this. And really, the way we're going to do this is kind of a two-step approach. So we have the function that we're integrating, little f of x. The first step for how to calculate a definite integral is to figure out what the antiderivative is. So get the antiderivative. And then, once we have the antiderivative, we're going to put this vertical line at the end, which means evaluate. And we put our lower limit at the bottom, and we put our upper limit at the top from our limits of integration. All right, so this vertical line means evaluate. And then once we actually have our antiderivative, then in a separate step, we're going to take this top number in, plug it in. We're going to take the bottom number, plug it in, and then we subtract. And that's really what this vertical line means. It means do the evaluation. So this is our evaluate line. All right. So just a little bit. So we're going to come back to this process here. We'll try a couple examples. But just another comment on the notation. So we've seen indefinite integrals. This is the notation we used for finding antiderivatives. So we have the integral sign, the function we're integrating, and then dx. And for an indefinite integral, there's no numbers on our on our integral sign here. There's no limits of integration. And so when we calculate an indefinite integral, the result should be a function, and we want to make sure we use plus c here. Now for a definite integral, very similar notation, but now we have these limits of integration, and so when we get our final result, the final result should be just a number. There shouldn't be any variables. We're not going to be using plus c here, so the final result should just be a number. And so for calculating definite integral, we don't need to use plus c. And actually, if we kind of go back up to this process here, this process works for any antiderivative. So we could have our antiderivative plus c, and then when we do the subtraction, the c's would just get canceled off. So it's easier to just take c to be 0, and we don't have to worry about it then. All right, so like I said, we're just going to practice calculating these types of these gadgets, these definite integrals. And we're going to see later on how to interpret what this is actually calculating. So I just want to get a practice on how to calculate these. So let's look at a couple. So let's look at this first integral. So this is a definite integral. So we're looking at the function x squared, and we're integrating from over the interval from 1 to 2. So the first step for calculating a definite integral is to get the antiderivative of the function. So we want the antiderivative of this x squared function. So what would our antiderivative be? Well, we're starting to learn some antiderivative rules. And if we do this, we can just use regular power rule. So our variable is x. We add 1 to the exponent there. We take that new exponent, we flip it, put it in front, so we end up with 1/3 x cubed. And then for definite integrals, we're going to put this vertical line, which means evaluate. So we don't need to use plus c here for our definite integral. And so this is the first step. We get our antiderivative. And when we do this, we do need this vertical line, which is telling us to evaluate. Then the next step is to actually do the evaluation. So when you go to do the evaluation, it helps kind of get some parentheses set up. And this will be for what we get when we plug the top number in. And then we're going to subtract and then get another set of parentheses going. And this will be what we get when we plug in our lower bound. All right, so let's take the upper number, the upper limit here. Let's plug it in. And when we do that, we get 1/3 times 2 cubed. And then when we plug that lower limit in, x equals 1, we're plugging it into that same antiderivative. We're going to get 1/3 times 1 cubed. And we're done. Now we can simplify this. So this is just 8/3. And minus 1/3, which is just 7/3. And that's the value of this definite integral. So again, we're going to see how to interpret what this number actually represents. There's going to be a couple different interpretations. Kind of spoil it a little bit. This is going to represent area. But right now we're just getting practice how to do this. So let's try another one. We'll save this one for class. So let's look at let's do that one. So let's look at this one. So the function we're integrating is e raised to the power t, and our upper limits are, or our lower limit is -1, and our upper limit is +1. All right, so we've got a definite integral here. First step is get the antiderivative. So what's the antiderivative of the exponential function? Well, it's just the exponential function. So it doesn't look like we're doing anything, but we are. e raised to the power t is the antiderivative of e raised to the power t. And then we put this vertical line at the end, which is telling us then we're going to evaluate this antiderivative. And the only thing we got to be careful of here, we're using variable t, so we just want to make sure we're saying t in our antiderivative and our limits of integration. All right, so we get our antiderivative, and now we're ready to evaluate. So when you do this, for more complicated antiderivatives, it usually is a good idea. Just kind of set up the parentheses and then put a subtraction sign in the middle. And in the first set of parentheses, that's what we'll get, what we'll put in our, when we evaluate our antiderivative for t equals 1, we'll fill it in there. And then for the second set of parentheses, that's where we'll evaluate t equals negative 1. All right, so let's plug t equals 1 in to our antiderivative. And when we do that here, we get e raised to the power 1. And then let's plug negative 1 in. And we'll fill that in right here. And we get e raised to the negative 1. And if we simplify, not really too much to do. We just get e minus e to the negative 1. And that's our antiderivative. All right, so this is the idea behind doing these definite integrals. So right now we're just seeing how to calculate these gadgets. We'll see later on what this actually represents. And again, it's kind of related to area, and we'll see exactly why. Now, one thing about this fundamental theorem of calculus, pop back up, we do need our function to be continuous on the interval that we're integrating. So we're essentially what we're going to be doing is we're kind of going throughout this entire interval. So we're looking at the values of our function throughout this entire interval. And so we need the function to be continuous on that entire interval, not just at the endpoints. It has to be continuous everywhere. And so the last example that we'll look at, part of example 1 here, this integral of 1 over x squared from negative 1 to 3, this one doesn't fit the bill. Because what we're doing is we're integrating the function 1 over x squared, and we're going from negative 1 to 3. And so for right now, this integral is undefined. And the reason is because this function 1 over x squared is undefined at x equals 0, somewhere in the middle of this interval. So it's undefined at x equals 0 because we would be getting division by 0 there. And 0 is in the interval, going from negative 1 to 3. So it's okay if our function's undefined at an x value, if that x value is not in the interval. But in this case, 1 over x squared is undefined at x equals 0, and 0 is actually inside that interval. So we can't actually calculate this. You'll see in Calc 2 how to do something like this. But for right now, we're going to kind of avoid things like this. All right, so we'll look at some more examples of calculating definite integrals, and we'll also look at some properties. So we'll see you then. Bye-bye.